Okay, so our next talk's on VMSL, a separation logic for mechanized robust safety of virtual machines communicating above FFA. And Zongyuan is going to give a talk.
Thanks. Hi everyone, I'm Zongyuan from Aarhus University. Today I will be presenting VMSL, a mechanized separation logic for reasoning about the combination of known and unknown communicating virtual machines. So first, let me introduce some background on virtualizations. In a system where one hypervisor hosts multiple virtual machines, the hypervisor is a component that has high privilege and manage hardware resources like CPU cores, registers, and memories. And its main functionality is to distribute the resources to virtual machines in the way that VMs run as if on bare metal. In addition, the hypervisor is supposed to provide isolation between VMs. It means that VMs are not supposed to be able to interfere others by touching other VMs' private resources. For instance, in this system in which we have 3 VMs, the hope is that even if the VM2 is hijacked or the code running on it is unknown, it's not able to manipulate private data of the other 2 VMs. However, it is usually not an absolute isolation that hypervisor provides. The hypervisor usually allows virtual machines to communicate with each other via message passing or shared memories. The communication is achieved by allowing VMs invoking a set of hypercalls provided by the hypervisor. Similar to the system calls that are provided by the operating system, the idea is that low-privilege VMs can request hypervisor to perform high-privilege operations, like context switching or establishing communication channels. However, this communication mechanism provided by the hypercalls poses a big challenge on whether the design of the hypercall interface is secure enough to not break the desired isolation properties. The overall goal of our work is to reason about VMs using hypercalls in such scenarios where some VM's code is unknown. And in this work, we focus on a specific hypercall interface called FFA that is available on ARM machines. So memory management is a key security property that we hope a hypervisor can provide by controlling memory access of VMs properly. Let's take a closer look at how it works. If the virtualization is enabled in the system, then in addition to the regular memory address translation managed by the operating systems, or in our case, VMs, there will be a followed-up extra stage managed by the hypervisor. Similar to how OS controls the first stage translation, in the second stage translation, the hypervisor maintains a page table for each VM in this privileged memory, and therefore controls which pages a VM can access to. This figure shows an example of the second stage translation. Each VM has its own pages in this virtual memory, and these pages are mapped to the physical pages of the same color. Notice that the 2 virtual pages in the middle are mapped to the same physical page, which could be the consequence of memory sharing hypercalls. It illustrates that this mixed color page is being shared between the 2 VMs, and thus the 2 VMs can communicate via this shared page. The first goal of this work is to reason about the behaviors of VMs communicating via channels like shared memory. To do so, we build a separation logic. Because it's quite intuitive to relate memory management concept and functionalities provided by the FFA interface I mentioned earlier with well-established separation logic concepts. For instance, communicating virtual machines correspond to cooperative threads. And permissions to access or shared memory is a notion of ownership. The action of sharing memory pages corresponds to transferring ownerships. And memory isolation is a notion of separation. Overall, the contributions of our work includes, first, a formalization of a substantial part of ARM's FFA specification as an optional semantics. The language we consider here is a toy assembly language, but with an FFA instruction which can be used by the VMs to invoke FFA hypercalls. On top of the semantics, we developed VMSL, a separation logic for modular reasoning about VMs with communications. Our logic has fairly standard notion of whole triples used for sophistication of programs and proof rules. For instance, this is a sophistication for a move instruction. The move instruction is moving the value of R2 to R1. So in the precondition, we have the ownership of the two registers where the register R2 has value of 42. And in the postcondition, the value of R1 is also updated to 42. In the logic, we apply the technique called logic relations to capture and prove that the FFA hypercalls do not break the isolation properties. And it allows us to reason about the combination of VMs running known code and those running unknown code. In addition, the logic, its soundness proof, logic relations, and the representing example we verified are all mechanized in Coq with the IRIS logical framework, which gives us advanced features like high-order goal state and guarded recursion for free. So let's first see how we achieve VM modular reasoning of context-switching FFA hypercalls. The VMs can pass the control of the CPU back and forth with hypercalls run and yield. In this example, VM0 is the so-called primary VM, which among all VMs can evoke the run hypercall to pass the control to any other VMs. In this case, VM0 is running VM1. The invocation works by VM0 executing the HVC instruction with arguments saved in registers. One can think this as a function call following some calling conventions. Other VMs like VM1 are called secondary VMs. They can only invoke a yield hypercall to yield back to the primary VM. Since we want to reason about only one VM at a time, like how we reason about threads locally in concurrent separation logic, we need a way to specify a protocol describing the interaction between the two VMs. The protocol is usually formulated using resources in separation logic, describing how ownership of the resources are transferred between the two VMs. In concurrent separation logic, the resource transfer is usually done via invariant. Well, in our logic, we introduce a more lightweight solution called resumption conditions, which is more suitable to the sequential setting we are considering. The idea is, when reasoning about VM0, the VM0 can transfer resource P along with a resumption condition Q to request resource Q from VM1. And VM1 can take P and have to give back Q when yielding. Which could, the VM0 thus can obtain the ownership of the Q, which could be updated by VM1 from P, and then continue the execution. The resumption condition is higher order, which means one can put one resumption condition into another, and the support guarded recursion, which are quite powerful and expressive and sound thanks to IRIS. With these features, one can define a recursive resumption condition to reason about a ping-pong example in which two VMs keep yielding to the other. Now let's add some more memory sharing hypercalls to the example. Before running VM1, VM0 invokes another FFA to share a memory page P with VM1. VM1 then retrieves access to the page P and writes value 42 to it. VM0 finally reads from the page, and we want to prove that the value it's read is 42. In the logic, we have standard points to assertions for the memory and page tables, and they can be transferred via the resumption conditions. When running VM1, VM0 transfer the memory and page table points to predicates along with the resumption condition requesting the page P has value 42 when VM1 yielding back. The VM1 then retrieves the access, updating the page table resources from P points to 0 to P points to 0 and 1, and then writes the 42 to the page. Now let's think about a much more challenging example by adding just one more hypercalls, Before reading the value from page P, now the VM0 runs the unknown VM2. Here, we still want to prove that the same specification of VM0 holds. And it should be true if the isolation property is provided in the system. In another word, if we can prove that the specification in a setup with only VM0 and VM1, then we should be able to prove it even if the unknown VM2 is added. In fact, we should be able to prove a variance of this example in which VM0 runs VM2 at any point. The intuition is that since VM2 has no access to the shared page P, it should never get the ownership of page P. We call such property of the system as robustivity. So we capture and prove the robustivity property in the logic using a technique called logic relations. Logic relations are usually used to give semantics meaning of types for typed languages, which can be used to capture many properties of the language like safety, non-interference, and so on. In our case, we have a unary uni-type logic relations for our toy assembly language. The overall behind the definition of the logic relation is that a VM can only change memory it has or can get access to. This intuition also shows up even if we only look at the shape of the main theorem. The theorem is parameterized by the state of the page table and in-flight memory sharing transactions. The state of page table indicating which pages that VM has access to, and the transactions indicates which pages the VM can get access to. One challenge is that we have to account for the footprint resources required by all the FFA hypercalls. And with those resources in hand, we want to prove that it is safe to run the VM. So we proved two logic relations for unknown primary and secondary VMs. We need two logical relations since the capability of the primary VM and secondary VMs are different. In particular, because the primary VM can run any arbitrary secondary VMs. But these two logical relations are compatible, which means our logic supports reasoning about any amount of unknown VMs. So in conclusion, we formalized a substantial part of the FFA specification as implemented by Google's half-name hypervisor. We developed a separation logic and defined two logical relations. This tool allows us to verify some key scenarios of VMs using FFA hypercalls in the presence of adversarial unknown code. Finally, all of the results are mechanized in Calc and is available online. That's all. I'm happy to take questions.
Hello, Yufang Chen from Academia Sinica. Very nice work. My question is that this kind of verification is usually take a lot of manual efforts, and in particular if you do it at the source code level. And do you have any perspective that how far is it from making this to a little bit more automated? This kind of proof work.
Yes, I think there's some works on trying to automate this kind of separation logic reasoning, also in Aarhus. So I think some of those approaches are applicable into our work.
Yes. Hi, I'm Dave Holland from Galois. I was wondering, so the interface here is very, very similar to L4 hypercalls or L4 message passing. Have you thought about how this interacts with, for example, using SCL4 as your base layer?
Sorry, can you repeat the last sentence again?
Have you thought about how this might interact with using SCL4 as your effectively as your hypervisor?
Sorry, I didn't get the question. So you're asking about the difference between the hypercall interface we're considering and the one in SL4?
Yeah, or to what extent your work here is applicable to the SEL4 interface?
I'm not very familiar with the SL4 interface. But here, I think our interface is quite rich in the sense that it supports many different memory sharing actions.
Right, okay.
Hi, I'm Ike from Radboud University Nijmegen. I was wondering kind of how the rules look in the logic when you yield or run a different VM. So what happens, do we have like a global view of all the resources in 2 threads and some of them get locked up somehow? How does that work?
Yes, so in our logic, most of the resources are indexed by the VM ID, in the sense that those are all global resources. So you need to specify like which, for example, which VM this resource belongs to. Yes.
Okay, thanks.
So I have a couple of questions. So in the examples you presented, it looked very much like coroutines where you're sort of going in and then your assumptions coming out, but that isn't really concurrent in some sense. So is that just for the examples you presented, or is it all sort of that coroutine style? Do you sort of have genuine concurrency?
Yes, because we don't have concurrency in our setup. Yes, so it's yes, indeed quite like like a coroutine, and that's how the run yield hypercalls works. Yes, but if you consider concurrency or interrupts, right? For example, if you have interrupts, then there's a different way to switch between the 2 VMs. Yes.
Right. Okay. So then things like virtual functions and sort of the hardware where it directly writes into your memory is sort of out of scope at the moment as well. Is that? So like on a network card, you'd have a virtual function that writes directly into your pages. That's kind of, that would be concurrent as well, so that's not covered at the moment.
Sorry, you're supposed to...
Sorry. Like on a, you'd have a, network cards can write directly into your memory if you set it up right. So that's sort of, that would also be concurrent, so not covered yet.
Yes.
Yeah.
Yeah.
And then, so is this sort of reusable to some like Intel, or like is it completely tied to the FFA thing, or do you think it's sort of reusable across some other platforms?
I think this approach of using a logic relation to capture the raw safety can also apply to any other interface, yes.
Cool. Okay, if there's no more questions, let's thank the speaker.